In this podcast episode, Neil deGrasse Tyson hosts a wide-ranging conversation with Nobel laureate Adam Riess, exploring the nature of the universe's expansion, the discovery of dark energy, and the persistent tensions in cosmological measurements that challenge our understanding of fundamental physics. They discuss the methods by which astronomers measure cosmic distances, the role of Type 1a supernovae as standard candles, the Lambda cold dark matter (LCDM) cosmological model, the mystery of dark energy, and the ongoing scientific debates about the universe's fate and the discrepancies in measuring its expansion rate. Adam Riess and Neil deGrasse Tyson begin by explaining the challenge of measuring astronomical distances, which is crucial for mapping the universe's expansion history. Parallax measurements serve as the most direct method for nearby stars. By observing the apparent shift of a star's position against distant background stars at opposite points in Earth's orbit, astronomers can calculate precise distances for relatively close stars. However, parallax is limited to stars within the Milky Way and cannot reach farther galaxies. To extend the distance ladder, astronomers use standard candles, objects with known intrinsic brightness. Cepheid variable stars, which pulsate with regular periods linked to their luminosities, were the classical standard candle for measuring distances within and just beyond the Milky Way. But to probe the far deeper, cosmological distances necessary to observe the universe's expansion over billions of years, astronomers turned to Type 1a supernovae, stellar explosions that reach luminosities billions of times that of the Sun. Type 1a supernovae arise from white dwarf stars in binary systems that accumulate mass from a companion star. When the white dwarf's mass approaches the Chandrasekhar limit, approximately 1/4 times the Sun's mass, it undergoes a thermonuclear explosion with remarkably consistent brightness. This homogeneity makes them reliable standard candles across vast distances. By comparing their observed brightness to the intrinsic luminosity, astronomers can deduce their distances, allowing a mapping of the universe's expansion rate at different epochs. Importantly, Riess emphasized that the discovery of cosmic acceleration did not require knowing the absolute luminosity of these supernovae, but rather their relative brightness over time. This relative comparison revealed that, contrary to expectations, the universe is not slowing down its expansion due to gravity, but is instead accelerating. Adam Riess recounts how in the 1990s, cosmologists sought to determine whether the universe's expansion was decelerating, as gravity from matter would dictate, or would continue forever. He and others measured the light from distant Type Ia supernova to trace the expansion history. The key surprise was that the data indicated an accelerating expansion, implying the presence of an unknown force or energy driving the cosmos apart. This discovery revived Einstein's cosmological constant, an energy density inherent to space itself that produces repulsive gravity, now dubbed dark energy. Despite the name, the physical nature of dark energy remains a profound mystery. Riess highlights that while dark energy explains the observed acceleration, its origin, properties, and evolution over cosmic time are still open questions. The discussion turns to the prevailing cosmological model, ΛCDM, which incorporates dark energy, L, and cold dark matter, CDM, as major components of the universe's total mass energy content. Observations of the cosmic microwave background, CMB, the relic radiation from the Big Bang, along with galaxy surveys and supernova data, all cohere within this model, suggesting a universe composed predominantly of dark matter and dark energy, with ordinary matter making up only a small fraction. Riess explains how satellite missions such as WMAP and Planck have provided detailed baby pictures of the early universe reflected in the CMB. These snapshots allow cosmologists to precisely infer the composition, geometry, and initial conditions of the cosmos shortly after its birth. A central topic is the measurement of the Hubble constant, the rate at which the universe is currently expanding. Two main approaches yield discordant results. One approach uses local measurements based on the cosmic distance ladder, parallax, Cepheids, Type Ia supernovae, to directly measure distances and expansion rates in the nearby universe, yielding a higher value around 73 to 75 km per MPC. The other relies on CMB observations and the LCDM model to extrapolate the expansion rate from the early universe to today, resulting in a lower value near 67 kilometers per second per MPC. This discrepancy, known as the Hubble tension, exceeds the combined measurement uncertainties, suggesting that our current understanding may be incomplete or that unknown physics is at play. Riess discusses how the James Webb Space Telescope has confirmed the local measurements with even greater precision, strengthening the case that this tension is real and not due to observational errors. The podcast explores theoretical ideas to resolve the Hubble tension. One notion is that dark energy might have evolved or undergone phases, such as an early dark energy episode shortly after the Big Bang, altering the universe's expansion history in a way that could reconcile early and late-time observations. Another possibility is more subtle physics, like interactions involving new particles or magnetic fields in the early universe plasma, which could affect the CMB imprint. Riess stresses these explanations remain speculative and might invoke new entities or mechanisms akin to tooth fairies, reminding listeners that the community is cautious but open to revolutionary changes. The episode also touches on alternative approaches, such as revisiting assumptions in the application of general relativity to an inhomogeneous universe. Neil and Adam reflect on the nature of scientific progress, emphasizing how anomalies and tensions, like the orbit of Mercury at the dawn of general relativity, can signal the need for deeper theoretical revolutions. They caution against drawing premature conclusions, likening the current situation to the slow but profound transformation from geocentric to heliocentric models centuries ago. Riess recalls how the discovery of dark energy also resolved an earlier age crisis, where some stars appeared older than the universe. With acceleration accounted for, the age estimates became consistent. This underscores how new insights can reshape multiple areas of cosmology. The conversation turns hopeful with new powerful observatories coming online. The Nancy Grace Roman Space Telescope, dedicated to studying dark energy, the Vera Rubin Observatory, set to survey vast swaths of the sky and discover millions of supernovae and asteroids, ongoing CMB experiments like the Simons Observatory, and gravitational wave observatories such as LIGO all promise to provide richer datasets and more stringent tests. Riess underscores that multiple independent teams measuring the Hubble constant with different techniques consistently find the local expansion rate to be higher, adding confidence to the tension's robustness. The new instruments and observatories are expected to refine measurements, test theoretical models, and possibly uncover new physics. A notable point made is the democratization of scientific data in modern astrophysics. Unlike earlier eras when crucial photographic plates were privately held, today's data and observations are publicly archived, enabling independent verification, cross-checking among competing teams, and accelerating progress. This openness helps minimize errors and groupthink, although some dissenting voices remain on the edges of mainstream cosmology. Finally, the hosts discuss the paradox of designing next-generation telescopes and experiments without fully knowing what to expect. Astronomers rely on current best models, but also build in flexibility to discover unforeseen phenomena. This balance between targeting hypotheses and embracing discovery space is a defining feature of frontier science. Riess expresses deep satisfaction in the evolving pursuit of understanding, acknowledging that key cosmological questions transform as knowledge grows, often revealing questions no one thought to ask previously. This dynamic ensures that cosmology remains a vibrant, continually advancing field driven by observation, theory, and a dose of cosmic humility.